The last part of chapter 10, we're going to talk about some of the properties of bonds that can lead to some really interesting physical and chemical properties of molecules themselves. And so we're going to look at first at an example of a phenomenon that we're all pretty familiar with, that oil and water don't mix, and that they'll separate into distinct regions, and that we might think, oh, well, that's just a density related thing, that oil's less dense than water. And while there is a density difference between them, it turns out that there's more to it than just that. It's something about the water molecules themselves, and that they will bunch together and that they will expel the oil molecules. And if you shake it up, that they will continue, the water molecules will eventually expel all of those oil molecules from, and all the water molecules will come together. So we can explain that by something about the bonds and the properties of the bonds of water molecules. So there's something about the geometry of the water molecules, and there's something about the electronegativity, so a concept we haven't talked about, but we're going to talk about next, that can lead to something called polarity, bond polarity, and the polarity of molecules as well. So let's dive into it. First, we need to talk something about a concept called electronegativity and what that means. And that electronegativity is a description for an atom's attraction for electrons. And when we have two atoms that are part of a covalent bond and they're sharing electrons, some atoms have a greater affinity or attraction for those electrons than others. This is also related to some of the patterns that we talked about in chapter 9 about like the atomic size, that elements in the upper right part of the periodic table had a smaller atomic radii or smaller atomic size compared to those elements that are in the lower left part of the periodic table. And this was also a trend where we talked about, hey, these are the ones that were down here in this lower left had greater metallic properties than ones in the upper right part of the periodic table in the main group. Remember that we're just looking at main group elements here, and of course we're excluding our noble gases. Okay, so let's look at this negativity scale. The negativity scale was designed or first described by a pretty important chemist. His name is Linus Pauling. He actually is super important in biology too. He made some really important discoveries. His contributions are amazing to chemistry and biology. He came up with this way of describing electronegativity, and he used a relative scale. He said that he defined fluorine as having the greatest electronegativity on the periodic table, and then he assigned that a value of 4.0, and then he compared all elements in the main group compared to fluorine, and he assigned them a value. And so things that have numbers closer to 4 are more electronegative, and things with numbers that are lower or farther away from 4 have less electronegativity. And we can see that scale down here on this chart. So strong electronegativity is close to 4 and numbers close to 4, and weak electronegativity values of 0.7 or close to 0.7. Okay, so if we have two elements that are in a covalent bond and they are sharing electrons, so let's say we're over here on the right-hand side of the periodic table, we're talking about nonmetals and we're talking about hydrogen, that if we have them bonded together in a covalent bond where we're sharing electrons, it turns out that they may not be sharing those electrons equally. And so we can say that some elements have a higher electronegativity value, and so they are more electronegative, and so that would mean that the electrons are more greatly attracted to that particular element. And what do I mean by the electrons? I mean the electrons that are in that bond. Those shared electrons are spending more time closer to one of the atoms than the other. So let's look at a particular molecule. where this is true, and that would be a water molecule. And so if we look at the particular bond, the covalent bond that is linking an oxygen and a hydrogen together within the water molecule, that pair of electrons, they're not being shared equally. So that bonding pair of electrons, with the oxygen being more electronegative than the hydrogen, that means that on average, the shared electrons in that bonding pair are more likely to be found towards the oxygen. And so that leads to something that we call a dipole moment. So a dipole moment is the word or the description for this particular phenomenon, where we have one of the atoms within the bonding pair has a greater affinity for the electrons than the other. And so the dots here represent the probable location of those bonding pair electrons at any given point in time. And because they're spending more time over by the oxygen, this leads to a partial charge difference within the bond. So that's symbolized by this little delta symbol, the Greek D letter, lowercase d. And notice how it's a delta minus and a delta plus, representing that it's a slight negative charge and a slight positive charge on opposite sides of this bond. So the oxygen atom's getting a larger share of the negative charge between that bond than the positive. And so that's because, remember, electrons have a negative charge. So if electrons are spending more time towards one of the atoms, then it's going to be a little bit more negative on that side. Okay, so this uneven sharing. So uneven sharing is what's called a dipole moment. So a dipole moment is an uneven sharing of electrons in a bond. So we can use this concept of dipole moment and whether a dipole moment exists to describe the character of the bond. And so a bond character is a way of classifying a bond. And we've already talked about bond classifications. We've talked about ionic bonds, where we've got two ions of opposite charges that are attracted to each other. And we've talked about sharing electrons, which we called a covalent bond. So now we're going to find out that these covalent bonds can also have equal sharing or kind of unequal sharing. So let's talk about how that's related to electronegativity. So it turns out that the greater the electronegativity difference between the two elements or the two atoms, the types of atoms that are in the bond, can result in characterizing the bond. So let's look at some examples. I'm just going to pull them all up real quick with their electronegativity values so we can compare them. So all of our examples here are going to involve chlorine. So we're all comparing with a chlorine example. And in the first example, we're comparing two chlorine atoms. So this would be Cl2. And when we have two chlorine atoms, they both have the same electronegativity, and according to the table, that electronegativity value is 3.0. And so 3.0, if I wanted to know what the difference in electronegativity is between these two, I would subtract 3.0 from 3.0 and I get a value of 0. Well, there's no difference in electronegativity. And so this particular bond is not polar at all. There's no unequal sharing. They're sharing completely equally. How about with our sodium and our chlorine? Well, that's a pretty big difference. We've got 3.0 and we've got 0.9. And so the difference between those two values is 2.1. That's a pretty significant difference. This is a superpolar bond. And in fact, it's so polar that we're not going to call it a covalent bond at all. How about between hydrogen, another nonmetal, and chlorine, also a nonmetal? Well, the difference between those is 3.0 is for chlorine, the electronegativity value for chlorine, minus 2.1 is the electronegativity value for hydrogen, and so the difference in electronegativity, the delta En, would be 0.9. And so that's kind of in between those two values. All right, well, let's look at this, because I think this table really helps us to be able to identify what's the bond character or bond type. So let's look at this table. This table shows us, it says the effect of electronegativity difference on bond type, and it shows us 3 bond types. It shows us purely covalent, so pure covalent, which is also going to go by the name nonpolar. We have a type called polar covalent, so they're sharing electrons, but they're not sharing them equally. And then we have a bond type that we've seen before, where the electronegativity difference is so great that an electron's actually going to be transferred. It's not going to be shared, and we're going to result in an ionic bond. So in our first example that we had on the previous slide, we can see our 2 chlorine atoms, and we can see the electronegativity difference of 0, and that they are completely shared equally. This is a pure covalent bond. And so we can see that this falls under this category, this range of 0 electronegativity difference of 0 to 0.4, and that anything in that range, we're going to say they're sharing those electrons pretty darn equally, and that is a purely covalent bond or a nonpolar bond. When we have values that are really great, large differences greater than 2.0, we're going to say that those electronegativity differences are so great that the electron's going to be transferred and is not going to be a shared covalent bond, no sharing of electrons. Electrons are going to be transferred. We're going to result in some ions, and then those ions are going to be attracted to each other, which we call an ionic bond, not a covalent bond. It's these ones that are in between, these intermediate ones, so an electronegativity difference of 0.4 to 2.0, those are the ones that are going to result in a shared sharing of electrons, so a covalent bond, but they're not shared equally, and so therefore we're going to call that a polar covalent bond. And just remember that this is like, this bottom diagram is kind of helpful because it really helps us to see that there's a continuum to the values. And so if we're talking about polar covalent bonds, that some covalent bonds are very polar and other covalent bonds are not as polar. So an electronegativity difference of, let's say, 0.7 is not nearly as polar as an electronegativity difference of, let's say, 1.2 or 2.2 or something to that effect. Okay, so let's look at some examples where we can look at some values, some electronegativity differences, and we can characterize the bonds directly ourselves. So we're going to look at carbon and nitrogen. And so we're going to always, when we're calculating our electronegativity differences, our delta ENs, we're going to need our electronegativity chart so that we can have those values to compare. And we'll just put the first one, the larger number first, because it's kind of an absolute value kind of difference in the end. So if nitrogen has an electronegativity value of 3 and carbon has an electronegativity value of 2.5, then our electronegativity difference is 0.5. So where does that fall on our table? Well, it's here in this intermediate category. So this would be just based on the numbers within the chart. This would be a polar covalent bond. And if I was to look at it on the continuum, it's in the category, right? It's in this range, but it's not a really great electronegativity difference. Let's look at nitrogen and hydrogen. So nitrogen 3.0 and hydrogen 2.1. Now we're looking at an electronegativity difference of 0.9. Well, that's definitely greater, right? This one's a much more polar bond. It's also polar covalent by definition or by the chart, but this one is a more polar bond than the carbon-nitrogen bond. Let's look at the nitrogen-oxygen. So if I look at oxygen's 3.5 and nitrogen is 3.0, this one also is 0.5. So it falls again in that polar covalent bond category. All right. Let's now look at, it says polar bonds and polar molecules. So, right, previously we were just looking at a particular bond, but now we want to think about, well, how about the overall molecule? So, if we just have two atoms in it, that's one thing. We can just look at that single bond and we can say, well, is it a polar molecule or not? Well, what happens when we have more than just two atoms in the molecule? And can we say that it's a polar molecule just by knowing about one of the bonds? Well, it turns out we can't. So when we're talking about a molecule and whether the molecule overall is polar, we need to think a little bit more about it. We need to think about its geometry because we need to think about, does the whole molecule have a dipole moment to it, a charge imbalance within the molecule? So again, like I just said, if it just has the two atoms in it, like let's say the fluorine here and the hydrogen, then we know that there is a dipole moment where the electrons are being pulled more towards the fluorine. They're spending more time towards the electronegative fluorine. And so because there's just two atoms in there, this is a polar molecule. There's a charge imbalance within the molecule itself. Well, now let's look at things that have three atoms in them, some simple ones to look at. We'll look at carbon dioxide here and water here. And so when we're looking at a molecule that has more than just two atoms, we're going to again need to look at the geometry of the molecule. So it says for molecules with more than two atoms, it's more difficult to tell a polar molecule from a non-polar molecule because two or more polar bonds may cancel each other out. All right, well, let's go look at what that's going to mean. Okay, in order for us to do a little bit of comparison like this, I need to show you some of the notation that we used to show dipole moments, and that we're going to need to use some vector diagrams, which are often used in physics to show forces, and that they can be really instructive for us to try to identify when things are balanced and canceling out, and when there's kind of a net summative effect and they're not canceling each other out. So first, let's look at our model here, one that we've already seen for the uneven sharing of electrons between two atoms. And now I'm showing you the vector notation on top of that. And the vector notation is set up so that the arrow points in the direction of the negative pole. And just a little reminder of like the word for poles, right, is to think about the poles being at opposite ends of a line, and that if like the North Pole and the South Pole, that there's a line that connects the North and the South Pole, and that there's kind of a differential at different points of that line. So that's where that wording comes from. And for our example, for our dipole, it's meaning that there is a slight negatively charged pole and a slightly positively charged pole. And that the way that the vector is set up, that the arrow points towards the negative pole, and that the vector has a little plus at the positive side. So it's got a little cross on it, if you will. Okay, so this is kind of a little preview to see that, hey, this is the same geometry that we talked about earlier. And I'm just going to kind of point them out to you over here real quick. So earlier we saw, hey, there could be a linear. This would be example of a linear molecule. And this is looking at our central atom here and our two terminal atoms and looking at a linear molecule. It's also possible to have kind of an orientation that we saw, which was our planar, our trigonal planar. And it's possible to have a model where we have our trigonal pyramidal kind of arrangement, our bent orientation, and over here on the far right, our tetrahedral kind of orientation. And that the vectors here in this example are kind of showing how whether or not the vectors would possibly cancel each other out. Okay, let's go look at some examples because I think it's with the examples that it becomes more obvious to us. So let's look at carbon dioxide. And so carbon here is our central atom, and we've got our oxygens on either side. And that if we were to look at our electronegativity values, each of these bonds is polar. So the bond between the carbon and the oxygens here is a polar bond, so on this side, and also on the left side is a polar bond, and the electronegativity difference between them is 1.0. And in the end, in this case, our vectors would be oriented with the arrows pointing out. Whoops, that didn't go in the right place. I should have my positive there. They'd be pointing outward. But because we know that this is a linear molecule, and remember, how would I know that that was a linear molecule? A quick little recap on that is that this particular molecule has just two electron bonding groups. And when we have an element, a molecule with just two electron bonding groups, it's going to be linear. Okay, so because it has linear geometry, the dipole moment of one bond completely cancels the dipole moment of the other, and the molecule is nonpolar. Okay, so let's just look at this part right over here on the right, where it says, hey, carbon dioxide has polar bonds, but the molecule overall is nonpolar. And that's because the dipole moments cancel each other out. Okay, so this is definitely true because this molecule is symmetrical, right? It has a carbon in the center and an oxygen on either side. Okay. Let's look now at an example of polar bonds within a molecule that leads to a polar molecule. So in this particular case, we've got polar bonds again. So the bond between a hydrogen and an oxygen is a polar bond. And we have two polar bonds within this molecule. But remember that this molecule is not linear. This molecule actually has 4 electron groups, which gives it a tetrahedral electron geometry. But because it has the 2 lone pairs, it ends up in a bent molecular geometry. And it says here that water has 2 dipole moments that do not cancel, and the molecule is polar. So let's take a look at where the vector diagram is. Here's this vector diagram, and we can see that we've got our vectors showing the electronegativity dipole moments, and that these 2 vectors are not canceling each other out. And so there's a net overall polarity to this molecule. So it's negatively charged, slightly negatively charged on one side, and slightly positively charged on the other side. So the molecule is polar as well as having polar bonds. All right. So what are the two requirements for resulting in a polar molecule? So when is a molecule polar? Well, it definitely has to have some polar bonds. So if you don't have polar bonds, then you won't have a polar molecule. If there's a lack in symmetry in the polar bonds, so that's a great example. So in the case with the and when so I should say when could that happen? Well, if there are lone pairs in the molecule, like there are here in the water molecule, then you're definitely going to have a polar molecule. So sometimes it's a little confusing because sometimes students will look at the carbon dioxide and they're like, wait, but there's lone pairs out here, but those lone pairs are not on the central atom contributing to the geometry of it. So I just want to kind of point that out. So when you're looking for those lone pairs, you're looking for lone pairs that are on the central atom. That's what's affecting the geometry, resulting in dipole moments that aren't going to cancel. Okay, and then the other thing to look for is that sometimes there's not, that the central atom doesn't have the same type of terminal atoms. So if you have, like in this example, I've got a carbon with 4 hydrogens, and that the dipole moments in the end, in this 3-dimensional geometry, would all be canceling each other out. But in the case here with a chlorine, that wouldn't be true because now the electronegativity difference would not be all canceling each other out because there is a difference, electronegativity difference between a chlorine and carbon bond than there is between the hydrogen and carbon bonds. Okay, so this in the end can help us to explain that phenomenon that we saw before. So it turns out that hydrocarbon molecules, because of their geometry of having just carbons and hydrogens and all that tetrahedral geometry, that all of those dipole moments that exist within that, all those dipole moments of the bonds of the carbon-hydrogen bonds, they cancel each other out. And so they're non-polar molecules. Whereas the dipole moments within the water molecules do not cancel each other out. And so there's a charge imbalance within the molecule, which makes them to be polar. And so those water molecules with those dipole moments within the molecule results in them being attracted to each other, and it makes them sticky to one another. And so when they are sticky to one another, they start to expel those nonpolar molecules from their space. And that's what pushes those nonpolar oil molecules out of the water. Super cool. Okay, well, this can also help us in everyday chemistry to, if you will, design molecules that can help us do particular tasks, like soap. So soap is an amazing, I guess you could say, molecule that we have designed, but it's definitely based upon other molecules, biological molecules that we know work in a particular way. But let's just talk about how soap molecules work. So let's say after cooking some bacon in the microwave, the plate's coated with grease and oil, and if you want to wash the plate with only water, the plate remains greasy. However, if you add a little soap, the grease washes away. Why is that? Well, water molecules are polar, and the molecules that compose the grease and oils we said are nonpolar. So as a result, the water and the grease repel each other. But soap bridges that gap. And soap bridges that gap by being a molecule that has both properties. It has a nonpolar region, a nonpolar tail that attracts the grease and oil, and it's got a polar end to the molecule that attracts the water. So the polar head of the soap molecule strongly attracts water molecules, while the nonpolar tail strongly attracts grease and oil. And it's going to form these little structures that we call micelles. And the micelles, the nonpolar tails, combine and embed with the grease molecules, and the polar portion of the soap molecules all face outward and are surrounded by the water molecules, and that allows them to be washed away as you wash the surface of the plate. Some of you may have heard this micelles word before. It's pretty common right now in facial cleansers of talking about cleansing sort of things, and micellar waters for removing oils off of our skin. It's fun when little kind of biology and chemistry kind of words end up in everyday language. All right, we did it.